We're going to continue our study of computer programming by delving into number systems and encoding. We're going to learn how information is represented inside a computer using a combination of these two concepts. You already use a number system every day. It's called the decimal number system. In the number system that you use in your math class and in daily life, you have 10 different unique symbols that can be used to represent information. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And that's why they call it the decimal number system, because deci means 10. There are many different types of number systems. Most number systems have a base. For example, in decimal, the base is 10, because there are 10 distinct symbols that you can use. Binary, which is the number system most commonly associated with the computer, has 2 different symbols that can be used, because bi means 2. The 2 symbols are 0 and 1. Octal is a system that uses up to 8 symbols, 0 through 7, and hexadecimal means 16. Decimal 10, hexa meaning 6, that means 16 altogether. In that number system, you have 0 through 9 plus an A, B, C, D, E, and F. So, a number system, pretty simple, pretty straightforward. It has a base, has certain symbols that can be used to represent information. When you combine that with this idea of positional notation, then a number system really comes to life. You learned in your math class and throughout your entire academic career that you have a ones place, a tens place, and a hundreds place. But no one really ever explained to you why all of this works. No one probably came out and said, hey, you know, you're using a decimal number system and that it has a base of 10. Well, in addition to having a base, most number systems use what's called positional notation, which is to say that where the symbol is dictates its value. For example, in the decimal number system, you know that if the symbol is right here, it's in the ones place. If it's here, it's in the tens place. If it's here, it's in the hundreds place. So if we had a number, let's say 456, how does that actually work? What happens is you have the symbol 6 in the ones place, and it is multiplied by 10 to the 0, the base to an exponent of the position. So 1 times 6 becomes 6. The 5 is in the tens place, which gets its value by 10 raised to the 1. When you multiply that out, it's 5 times 10, which gives you 50. And then in the hundreds place, you actually have a symbol of 4 being multiplied by 10 to the 2, or 100. When you multiply 4 by 100, you get 400. When you add all these up, you get 400 plus 50 plus 6 equals 456. So, number systems represent numbers by combining symbols and putting them in positions that mean something. The value of each symbol depends upon its position and the base of the number system. So we get the ones place by virtue of the fact that 10 to the 0 is 1. We get the tens place by virtue of the fact that 10 to the 1 is 10, because anything raised to the 1 is itself. And we get the hundreds place by virtue of 10 raised to the 2 equals 100. So hopefully this gives you some idea of how the number system you use every day works. It's a combination of a distinct number of symbols that can be used and this positional notation in which the position in which the symbol is placed gives it its value. And this is exactly how you calculate the number from the symbols themselves. You're probably used to the term place value to describe this phenomenon. What you will notice is that in every number system, this rightmost value will be raised to the 0. It's considered the 0 position, and then the 1 position and the 2 position. So the way that place value is determined is by raising the base, in the case of decimal 10, to its position. Now, it can be confusing because the first position will have an exponent of 0. It's what we call in computer programming zero indexed, that the first thing starts with a 0, and then the next one's a 1, and the next one's a 2. So this pattern holds true for all number systems that employ position notation. Just remember, the place value is determined by taking the base and raising it to an exponent, and that the first position starts with a 0 and increments from there. The second position is a 1, the third position is a 2. So that's how you find the place value for any number system. Let's go through the number systems, the ones that are most important that you need to know. Base 10. So base 10 is the decimal number system. This is the number system that you're already familiar with. They call them digits, and they call it the decimal number system. Is inspired by the number of fingers that you have when you put your hands together. So whenever you want to think about the decimal number system, think about this graphic right here. You've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It may seem counterintuitive to start with 0, but remember, in the decimal number system and in these other number systems, 0 is an important number. A base 10 positional system uses 0 through 9. And remember, in a decimal number system, any fractional value needs to be preceded by a decimal, and then there's values to the right. So this is the system, the number system that most humans use. What about a computer? A computer uses what's called a binary number system. This graphic right here does a good job of describing what it's like. It's either a 0 or a 1 because a binary number system is a base 2 number system. This is used internally by most computers. This is that on-off switch that we keep talking about. 1 being on, 0 being off. So each digit in a binary system is called a bit, which is short for binary digit. So the system that computers use is called binary, which means binary digit. Bi means 2, which is basically saying that any value needs to be represented using the symbols 0 and 1 and 0 and 1 alone. Okay, why just 1s and 0s? Why can't the computer just simply use our decimal number system? Well, it comes down to the fact that the possible states of a transistor, those tiny little things that we're trying to pack onto a microchip, can only be on or off. They can only have a yes or no state. So a binary number system in which you can only have a 0 and a 1, an on-off, a true, false, a yes, no, turns out to be the perfect number system to be used inside the computer on these transistors. Either an electrical charge is flowing through this logic gate or it is not. So just remember, computers use binary. They use the 0 and the 1. I've got a cool video in here that I want you to watch. Just like with all my presentations, make sure after you watch the video, you go back, you watch any of the videos therein, and you answer any of the questions you find alongside the videos. The big idea: use binary to program machines. Part of the study we've done already in this class is about Konrad Zuse and how he discovered that using a combination of old telephone relays and this binary number system, he was able to make one of the first electronic computers. So all information is stored as a single bit, either a 0 or 1, a binary digit, and that's the smallest unit of information possible. Now, a bit by itself is not very helpful, but when you string a bunch of bits together, you can represent almost any kind of information. So the idea is, inside the computer, we want to combine these bits, these 0 or 1 values, into a big sequence that then can represent something much more meaningful. To demonstrate this concept, let's start with 4 happy bits. The first thing we need to talk about is that the place value in binary is determined differently. You're used to this being the 1's place, the 10's place, the 100's place, the 1000's place. But that doesn't work in binary. Because remember, the place value is determined by the base and the position of the symbol. Since the base of a binary system is 2, each one of the place values is going to be different. Remember, when you're determining position, this is the 0 position, the 1 position, the 2 position, the 3 position. Therefore, the place values in binary look something more like this: a 1, a 2, a 4, and an 8, because 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, and 2 to the 3 is 8. So now we know where the place values come from, but it's important to note that the bit only gets its place value if it's on. Remember, in a binary number system, we can only use 0 and 1, and 1 represents on. If a bit is on, it gets its place value. If it is off, it does not. If you look at the math behind this, what you'll see is we take the value of the bit, the 1, and we multiply it by its place value. That's why we get the 1. But if our bit is off, anything multiplied by 0 is 0, so we don't get the place value. What happens next is pretty straightforward. For all of the bits that are on, for all of the ones that get their place value, you sum them up. So all we do is we take all of our bits that are on, which have already been multiplied by their place value, and we add them all together. So 1 plus 2 plus 0 plus 8 gives us 11. So using 4 bits that can only be a 0 or a 1, we can represent the value 11 using the binary sequence 1, 0, 1, 1. We take the place values, we add them all together. And this is how you use binary to represent numbers. Once again, the binary sequence 1, 0, 1, 1 represents the number 11 because when this bit is on, it gets its place value, 2 raised to the 3. If this bit is off, 0 times 4 gives you 0. If this bit is on, it gets its place value, 1 times 2 to the 1. If this bit is on, it gets its place value, 1 times 2 to the 0. When you add all those up, you get the number 11. Terminology. You probably heard the terms bits and bytes before. Remember, a bit is an individual symbol, an individual digit that's either a 0 or a 1. It's, in essence, one of these light bulbs. A byte, however, is the combination, a sequence of 8 bits, just like you see here in this picture. A bit stands for binary digit, and then when you combine 8 bits together, you get a byte, which is short for binary term. So all these terms are logical. They come from somewhere. They all mean something. I have 2 different apps that, depending upon the platform that your phone is on, you can use to practice binary. I've done my best to try to explain to you how binary works, but these practice apps will really drive it home for you. If you have an Android, you can download and play the binary practice game. I also have tablets that you can use, so if you don't have a smartphone, just come see me. If you are on an Apple platform, if you're on iOS, you can download the Cisco binary game, install it, and let's see if you can build your binary skills. Another number system we want to talk about is hexadecimal. This is very popular for writing programs. This is something that most programmers know about. Remember, hexadecimal, that means 16. So there are 16 total different symbols that can be used in that number system. You've got the same ones as the decimal number system, the 0 through 9, plus to represent numbers up to 15, we have A, which represents 10, B, which represents 11, C, which represents 12, D, which represents 13, E, which represents 14, and F, which represents 15. So in this particular number system, there are actually letters that can be used in a position. So it's a little odd, but it's a very powerful system. And this is a system that many programmers use. Let me kind of break down the differences for you to kind of bring this full circle. If I'm using, let's say, the number 21, and I want to represent it in any of these number systems, well, I already know how I represent 21 in the decimal number system. I've got a 1 and a 2. 1 times the place value gives me a 1, and then 2 times the place value over here gives me 20. 20 plus 1 gives me 21. In a binary system, it's a little different. I would actually have a 1, a 0, a 1, a 0, and a 1. This is my 1's place, my 2 place, my 4 place, my 8 place, my 16th place. And by adding 16 plus 4 plus 1, I'd get 21. Now, this is where a lot of people get confused. Hexadecimal, I would have a 5 in this position right here and a 1 in this position because the place value in a hexadecimal system is 16 to the position. 16 to the 1 is just 1. So 1 times 5 gives me 5. In this position, my place value is 16 to the 1, which is 16. 1 times 16 gives me 16. So 16 plus 5 gives me 21. So it's a completely different way of representing information. Look at the different place values between these number systems. I have a ones place, tens place, hundreds place, thousands place, 10,000s place. In binary, it's pretty simple. 1, 2, 4, 8, 16, 32, 64. In hexadecimal, because of the number of combinations that having 16 different symbols allows me, I go from 1 to 16 to 256, and it really increases very quickly. So you can represent information using different number systems, and it's very powerful. So remember, bits by themselves aren't very powerful, but what makes binary really shine is that when you put a bunch of bits together, when you string together a sequence of bits, you can represent almost any kind of information. And that brings us to our next topic, which is encoding. A lot of information that we use day to day isn't numerical, it's actually text-based. And so encoding is something that allows us to store letters by using numbers. So I have a graphic here that hopefully demonstrates this concept. Let's say I have a letter that I want to store inside the computer. Let's say it's a capital M. Well, we don't really store letters inside the computer as letters. We store them as some encoded numeric value, and we use some scheme to decide for any given letter what numeric value should be used to represent it. This process of converting information to an easier form is called encoding. And one of the ways this is done inside a computer is that textual characters are encoded using a scheme that converts them to a number. Then that number is represented using a binary sequence. So we do not store letters as is. They are encoded first using some sort of scheme. I gave you this example right here. An uppercase M is encoded, converted to a numeric system where the uppercase M means 77. That the 77 and the uppercase M mean the same thing. And then 77 is then stored inside a computer using a sequence of ones and zeros like this. So that is how we use binary to store textual information. This process of taking a letter and converting it to an equivalent number and then placing it inside the computer as binary is encoding. That's what it's called. There is an encoding system that was the original encoding system used on the internet and was very popular called ASCII. And this was a character encoding scheme. So for any character, there was a corresponding number in binary sequence. This was how information used to be encoded out on the internet. And it was able to support only English, which obviously has its own problems. But let's take a look at this table. Make sure we understand this concept. Each character or symbol that you're used to typing on the keyboard is represented by a number. And then this number could be represented by a binary sequence. So if we look at the table, we'll see things like here is a capital A. The capital A is represented by the number 65. And the number 65 is actually a binary sequence 01000001. So I know it's kind of complicated, but it's important that you understand that this is what computers do. They don't store textual symbols. They store a binary version of a number which represents a character. There's a video in here, obviously. This is a tough concept. Make sure you watch this video. Make sure you can answer these 3 questions. Obviously, not everybody speaks or writes in English. So this ASCII encoding scheme really wasn't going to work for very long. I always use this to show students just how diverse our world is. This is I can eat glass and it doesn't hurt me in English. And this is the translation into many of the world's most popular languages. So we can't use an ASCII encoding scheme on the internet. If we did, we would only be able to support English and languages that used exclusively English characters. So we needed something that was going to help bring us together, that was going to give us global support. And it wasn't ASCII. The system that was devised was called Unicode. Unicode is the universal standard for encoding on the internet to support all of the world's languages. So in Unicode, we have something where there is a code point for every single character that exists in the languages of the world. And there is something called UTF-8, which is the most common encoding scheme that is used on the internet and inside computer programs. So Unicode is the encoding scheme that's used to support all of the world's languages. To get a better understanding of Unicode and what it is, make sure you watch this video. It's called the Unicode Miracle. I think it does a really good job of taking a very complicated concept and making it simple. Please see me with any questions, and I look forward to seeing you in class.